Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of our unit Semiconductors. Let's begin with today's class. In today's class we are going to discuss about the PN junction. It's a P-type material, N-type material junction. Let's have a look what PN junction is. When a semiconductor material such as the silicon or germanium is doped with the trivalent impurity on one side and pentavalent impurity on the other side, we obtain what we call as a PN junction. As you can see in the diagram too, that in silicon or germanium material, on the one of the side we have added trivalent impurity, and as we have discussed in the last class, that when we add a trivalent impurity to p or n type material or to intrinsic semiconductors, it will be having more number of holes, and holes behave as a majority charge carriers. And when we add pentavalent impurities, that means electrons will be majority charge carriers. And when we add this, when we combine this, when we make this two material on each other, then this is what we call as the PN junction. So when the depletion layer is sufficiently built up, when this region between this two, between the p type and n type, this is what we call as a depletion layer. So when the depletion layer is sufficiently built up, it prevents further diffusions of the electron from n side to p side and holes from the p side to n side, and this process is known as the diffusion. And this diffusion is due to the concentration gradient, and due to this diffusions, positive ions are left over in the n region and negative ions are left over in the p region near the junction, and this ions are the immobile. So what exactly is the situation happen is that we have a p type material over here, we have an n type material over here. When we connect this to p type material and n type material, the certain sorry, the certain electrons has been traveled from this to this, and certain holes has been traveled from this to this. So the situation arises that there is a one region is formed in between this PN junction, and that region is what we call as a depletion region, and they are having a certain ions, but unfortunately that ions are the immobile ions. Now remember our thought for using the semiconductors. Why do we choose this? Because we want that there must be a conduction when we want, and there should be a no conduction when we don't want it. But here the problem is there is no conduction. So when we thought that why we use this, it is not going to work until this phase, that when we want it should conduct, when we want it should not conduct. No, this is not happening. So while simply having p junction and n junction cannot work, that is what we understand up till now, because whatever the ions are there in the depletion region, they are the immobile ions, and we cannot have anything with this immobile ions. We are not supposed to do anything with this immobile ions. So the plane that is the separating this two region is what we call them as a junction, and near the junction, as we have seen this, the free electrons from n region migrate towards the p region, and the holes in this p region migrate towards the n region. Due to this immobiles ion on either side of the junction, an internal electric field is formed at that junction, and it is directed from n region to p region, because as you have seen this, that these are the positive charge carriers and these are the negative charge carriers. So always direction of electric field is from positive ion to negative ion, so it should look like this. And this is from the n region, this is from the this is from the n region to the p region. Please always do remember this thing. One time AIPMT has asked a question from this point, that what should be the direction of unbiased PN junction, direction of electric field for unbiased PN junction. A region of no charge carriers that is formed at the PN junction due to the combination of electron and hole is what we call as a depletion rear. And the thickness of the depletion layer is of the order of 10 to the power minus of 6 meter, which we call as an approximately 1 micron, so that it acts as a barrier. And the potential difference across the barrier is what we call as a potential barrier, or we could also call it as a contact potential, or we also feel it as a pseudo battery. The potential barrier for silicon diode or silicon is about zero point 0.7 volt, and same a potential barrier for the germanium, it is about zero point 0.3 volt. Please do remember this two value, it's a 0.7 volt for silicon and 0.3 volt for the germanium. Basically the potential barrier value lies in between 0.1 to 0.7, and this potential barrier value depends on the three parameters. One of them, it's the nature of semiconductor, another doping concentration, and third one, temperature of the junction. So if VB is the barrier and potential barrier and D is the thickness of the depletion layer, then the electric field intensity across the junction can be calculated based on this. This is E is equals to VB by D. We have a relation that E is equals to minus of delta V by delta R. It is the same relation we are using over here. And direction of electric field, it is from N site to P site. So this is the depletion region. What we understand. I hope this is clear. And even this is considered as a simply P N junction diode. This is simply the PN junction diode, and this is the symbol of the PN junction diode. And this generally, this node or this electrode is known as the anode, and this electrode is known as the cathode. In physics we represent cathode by K. In chemistry you might representing cathode by C, but in physics it's represented by K itself. So this is the symbol of a simplest PN junction diode. And you can see the construction of the PN junction diode, that on one of the side it's a P-type material, on the other side it's an N-type material. When they are connected back to back, a certain region is formed, and that region what we call as the depletion region, and they are ended with this two metallic contacts. And this depletion region contains many ions, but the problem is this all are the immobile ions. That means they are not going to move anywhere, and when they are not going to move anywhere, it means they are not going to conduct a current for us, which is our last requirement, and which is the answer that why do we use or why do we choose semiconductors. So at this point of stage we don't find anything in favor of the semiconductor, that yes, our decision to use the semiconductor instead of conductors and insulators are working. No, everything is not in favor of us. So let's see what happens next. But before we see the next situations, let's first look at certain quick questions. The barium potentials for silicon and germanium diodes are about, for silicon it's a 0.7 volt and for germanium it's a 0.3 volt. Next, in a PN junction diode made with the germanium, the thickness of the depletion layer, that is D, has been given, that is equals to 2 into 10 to the power minus of 6 meter, and the barrier potential is given, that is the delta V is given, which is equals to 0.3 volt. The strength of the electric field at the junction is, so this is E is equals to delta V divided by T, and that is equals to 0.3 divided by 2 into 10 to the power minus of 6. So this could be, it's a 0.3, which is equals to 3 by 10 into 10 to the power minus of 6. This is minus 6 here, so it's a plus 6 over here. So this is 3 into 10 to the power 6 divided by 1 by 2. 3 by 2, it's a 1.5, and this is equals to, this is 10, this is 10 to the power 6, so this 10, so 1.5 into 10 to the power plus 5 volt per meter, and direction from n side to p side. This would be the correct answer. So this is E, which is equals to delta V by delta R. I hope this is clear. Is it clear? Is it clear? Are you done with this? Are you? So do you understand what diode is first? What potential barrier is? Yes. And how do we use this diodes? Do you understand this? Are you sure? Do you have any doubts? Is there anything? Is there no? Great. Now let's discuss about the diffusion current and the drift currents. So first, let's discuss what diffusion current is. Due to the difference in concentrations of the charge carriers, holes from p side diffuses towards the n side, and electrons from n side diffuses towards the p side. So the movement of this charge carriers across the junction causes a current, and this current is known as the diffusion current. And this diffusion current is from the p side to the n side. I hope this is clear. Let's discuss what drift current is. If an electron hole pair is created in the depletion region, the electron is quickly pushed by the electric field towards the n side and the hole towards the p side. In this situation, an electron hole pairs are continuously created in the depletion region, and there is a regular flow of electron towards the n side and holes towards the p side. And there is almost no chance of recombination of a hole with an electron in the depletion region, and this makes a current from the n side to the p side, and this is what we known as the drift current. So I hope you are clear with what diffusion current and what drift current is. Let's have a look. Quick questions. The movement of the charge carriers across a junction that causes a current, and this current is known as the diffusion current. And the second one, it's the current from n side to p side. The current from n side to p side is called as the drift current. I hope this is clear. Is it clear? Great. Now let's look and let's understand what biasing is. Connecting a battery across the terminals of a diode is what we know as the biasing. And this biasing could be of two types. One of them is the forward biasing, and another one is the reverse bias. Now let's look at one by one what biasing and how to create a forward bias and reverse bias. So when we say it's a forward bias, or when we say it's a reverse bias, we are applying a potential difference across the terminals, and this potential difference applied across the diodes could be of two types. One of them would be a forward bias, another one would be a reverse bias. Now what forward bias mean? First look at this and we will back to that. In forward bias of a PN junction, the P side should be at a relatively higher potential compared to a N side, or we can also represent this like something like this, that this is the P side, this is the N side, that we already discussed, that this is considered as an anode, this is considered as an cathode. Yes, that we have represented, that when positive terminal of a diode has been connected with the positive terminal of the battery and negative terminal of the diode connected with the negative terminal of the battery. This can also be represented something like this. Look at this very carefully. This is P, this is N, and this is the P, this is the N. Yes. So if diode has been connected like this, if diode has been connected like this, that positive terminal of the battery connected with the P-type material and negative terminal has been connected with the N-type material, then this is what we call as the forward biasing of PN junction diode. Let's look at this. This all are the examples of forward biasing of a diode. Look at this. This P-type material has been connected to a 3 volt and this N-type connected with the 1 volt. So there is a potential difference of 2 volt, as well as this P-type material is connected to the higher potential. That means this is the case of the forward bias. Again, one more thing, this P-type has been connected with the minus 3 volt and this N-type has been connected with the minus 5 volt. So again, this P-type material is again at relatively higher potential. This is what we call as a forward bias. One more case, that P-type material connected with the ground, and when we connect it with the ground, it is at 0 volt. N-type material is connected at the minus 5 volt, and when this N-type is connected with minus 5, that means 0 is greater than minus 5, that means forward biasing. This next case is the P-type connected with the 2 volt, N-type connected with 0. So when P-type connected with 2 volt, it means it is at higher potential, and when it is at a higher potential, that means it is a forward bias. So please do not underestimate that if P-type, if it is a forward biasing, then P-type should be connected with plus voltage and N-type would be connected with the negative voltage. No, it is not such like this. What we want is that P-type material or the anode of the diode should be at higher potential as compared to the cathode. Yes, it is only the requirement. It could be such case that this is at plus 20 volt and this is at plus 15 volt. Yes, it is absolutely okay because this is still at higher potential. I hope you understand this. Yes. So in this case of biasing, in the forward case of biasing, the width of the depletion layer and barrier potential decreases, and as the width of the depletion layer and barrier potential decreases, it was much easier to flow of a current. So if V is the applied voltage and let's say VB is the barrier potential, then the net potential in forward bias is the V minus of VB, and it is having a low resistance connection, or it acts like a conductor. And for an ideal diode, please keep this in mind, for an ideal diode the resistance is 0, or for practical diode resistance is very less. So for ideal diode this is 0, and for practical diode this resistance is very less. So the flow of current, is mainly due to the diffusion of majority charge carriers, and it is of milliamperes. And the direction of this current is from P junction to the end, P type material to N type material. Sorry, I hope this is clear. So are you clear with the forward biasing? Yes, great. Now let's check what reverse biasing is. So in the reverse biasing of the diodes, as you can see, this is P-type material, this is N-type material. N-type material has been connected with the positive terminal of the battery, and the P-type of the material is connected with the negative terminal of the battery. So P region of the diode connected to the negative terminal of the battery, and N region is connected to the positive terminal of the battery. So what happens? Basically the thing will be that this is the P-type material, and here majority charge carriers will be the holes. And if majority charge carriers are the holes, all the holes will started accumulating here, I hope this is clear. You understand this fact. And so this depletion width, whatever you can see this, it has been increased to this because all the electrons will trying to accumulate over here on the this side, because this is the positive terminal and this is the negative terminal. So now as we connect this, this is the width of the depletion region after I have connected, after I have biased it with the reverse biasing. I hope this is clear. So this is the situation when we connect p-type material with negative terminal of the battery and n-type material with the positive terminal of the battery. So in reverse bias of the p-n junction diode, the p side should be at a relatively lower potential compared to the n side. So let's look at certain examples of it. Here you are seeing this, that p-type material is connected with the minus 2 volt and n-type material has been connected with the minus 1 volt. Yes, it is p-type material is relatively lower voltage. In the second case, it's a p-type material, it is at minus 5 volt and n-type which is at minus 3 volt. Here it's a p-type which is at minus 5 volt and n-type material which is at 0 volt. And in this case it's a p-type material which is at ground. When we say it's a ground, it is at 0 voltage. And n-type material will be at the 2 volt. So in this region, the width of the depletion layer and the barrier potential increases, as we have discussed in that diagram. So if such is the case, let's see what are other variations too. So let's suppose if V is the applied voltage and VB is the barrier potential, then the net potential in the reverse bias is VB plus V, and basically it's a higher resistance connection, or we can say it acts like an insulator. And for an ideal diode the resistance is infinity. We can say this is the open circuit situation. And for practical diode it is having very high resistance. So for practical diode it is having very high resistance, and for ideal diode it is an infinite, or we can say that this will work as an open circuit, that it will break the connection. So the current in the germanium diode is of the order of microampere, and silicon diode it is in the order of nanoampere. And in the reverse bias situation, the flow of current is mainly due to the drift of the minority charge carriers. So current in this bias is what we call as the reverse saturation current, or we can say it's a leakage current. And in this case the direction of the current is from n side to p side. I hope this is clear. So let's note certain very important thing, that we can say that diode is a unidirectional electronic device. It allows the current in the forward bias, and when applied voltage is greater than the barrier potential, and the current that flows across the junction of a diode due to difference in concentrations of holes or concentration of conduction electrons on either side is what we call as a diffusion current. And the current that flows through the diode due to the electric field is what we call as the drift current. I hope this is clear. Yes. So let's look at the application of a diode. What we are supposed to do is that this is the one of the battery, and this battery has been connected with the resistance R and PN junction diode. And as you can see this that this p-type material has been connected with the positive terminal of the battery, and this n-type material has been connected with the negative terminal of the battery. So as in this situation the biasing is forward bias, and as it is a forward bias connection, it will allow a current to pass through it. So for an ordinary diode, or I mean to say for an practical diode, this is equals to, this is the applied voltage E, this is the barrier potential, so this is equals to E minus VB divided by total resistance. When I say total resistance, because we know that for a practical diode there is a certain resistance, because in only ideology, or if we consider only the ideal situation, there is a zero forward bias current and infinite reverse bias current, but this is not possible in practical life. So we have considered RF, it's a forward bias resistance of the diode, and R is will work as an external resistance, and VB, it is the barrier potential. So for an ordinary diode, this I is equals to E minus VB divided by R plus RF. This is the current that will flow through this. I hope this is clear. So power developed across the diode, which is equals to VB into I. Power developed across the resistance, it's a E minus VB into I. And the minimum kinetic energy required by a hole to diffuse from P side to N side is, minimum kinetic energy is equals to E into VB. And in forward bias, the minimum kinetic energy required by a hole to diffuse from P side to N side, it is the minimum kinetic energy is equals to E into bracket VB minus VB. In reverse bias, the minimum kinetic energy required by a hole to diffuse from P side to N side, its a minimum kinetic energy is equals to E into bracket VB plus V. So all the above formulas are true even for an electron diffusing from N side to P side. Yes. So as we have discussed this for the holes, this is even true for the electrons as well. Have you noted it, or you want to note it? Noted it? Great. Now let's look at certain quick questions. The first question says that the resistance of an ideal diode in forward bias condition. Yes, resistance of an ideal diode is 0 in the forward bias condition. Next, in the middle of the depletion layer of a reverse bias PN junction. Yes, in the middle of a depletion region in the reverse bias PN junction diode, the potential is 0. I hope this is clear. Was it clear? Are you sure? Do you understand this? Have you? Great. Now let's discuss the VI. It means it's a voltage versus current. This is voltage versus current characteristics of a PN junction diode. This is VI characteristics of a PN junction diode. And when we plot this VI characteristics of a PN junction diode, basically what we are supposed to do is that there are two types of characteristics of PN junction diode, and that two characteristics are considered as the forward bias characteristics of a PN junction diode and the reverse bias characteristics of a PN junction diode. So first if I try to plot the forward bias characteristics of PN junction diode, this should be the circuit connection, that this is the diode and this PN junction diode has been connected for the forward biasing. So this P type material has been connected with the positive terminal of the battery, and this N type material has been connected with the negative terminal of the battery. To measure the current, we have the ammeter, and to measure the voltage across PN junction diode, we have voltmeter connected in parallel across the PN junction diode. So this is the circuit diagram to measure and to plot the VI characteristics. So we connect the external battery B with potential dividing arrangement to the PN junction as shown in the figure, and this PN junction diode is forward bias and practically Vk, it's a potential across the cathode, is equals to Vp. So as the forward bias voltage Vf increases beyond Vk, the forward current will start increases exponentially, and this is from milliampere. Yes, so if we, this is the graph between the forward bias voltage Vf on the x-axis, this is the forward bias voltage, and forward current If on the y-axis. As you can see this from here to here, the change in the current is very small, and generally this voltage, it's a point 0.7. Again, this is for silicon. This voltage is what we call as a cutoff voltage, or we also call it as a knee voltage. That after that voltage current increases abruptly. I hope this is clear. So this is the cutoff voltage, or this is what we call as a knee voltage, that this is the location, this is the point after which current increases at a very higher rate. Yes, this is basically that barrier potential which we talk about, that after this current start increasing. Yes, this cutoff voltage or knee voltage for silicon diode, it's a zero point 0.7, and for germanium diode it's a 0.3 volt. Yes, please do remember these numbers. We have already discussed it previously, but one more time here. Now let's look at the reverse bias characteristic of PN junction diode. When we want its a reverse bias characteristics, this is the PN junction diode. What I'm supposed to do is that this p-type material will be connected with the negative terminal of the battery, and this n-type material will be connected with the positive terminal of the battery. So to note the voltage across the diode, we have this voltmeter, and to measure the current we are having the ammeter. As you have observed it, that in the forward bias characteristic we have a milliampere, and in the reverse bias a current would be very less. That's why we have used a microampere. Yes, ammeter having very lesser range is used. Yes, so and we have a rheostat used over here, which due to which, or with the help of this rheostat, we can change this voltage. So as the forward bias voltage increases beyond Vk, the forward current increases exponentially, and that is what we have seen. Now if we increase the reverse bias voltage, and we are going to keep noting the reverse current. So if we plot this reverse current characteristics, then this would look like this. This is the reverse bias voltage, and this is the reverse current. As you can see this there is a very less amount of current is flowing through this. As please note it, this is in the microampere. Yes, so this is very less amount of current has been passed through it, and at certain stage has current occurred, which we call as the breakdown. Yes, so once you reach the breakdown, there is a sharp increase in the current, and this is what we call as a breakdown. Basically two types of breakdown can occur. One of them, it's an avalanche breakdown, and second one is the Zener breakdown. You just keep remember their names over here. We are going to discuss it in the coming slides, but please have a note this, that there are two types of breakdown can occur. One of them is the avalanche breakdown, and the another one is the Zener breakdown. So what happens that in the reverse bias situation, as we have considered this is a practical diode, a certain current will definitely flow, and this current is mainly due to the minority charge carriers, or we can say even due to the thermal energy that is available everywhere. That's why this amount of current has been flown, but again it's a very small. Ideally it would be a zero, practically it would be a very small in terms of microampere. So now you have seen both the characteristics. You have seen the forward bias characteristics, you have seen the reverse bias characteristics. Let's see this both in one of the image. Then this would be the situation that this is somehow for the ideal situation or very close to the ideal situation, that this is the voltage and this is the current. And as you can see, this from 0 to this voltage, this is what we call as the knee voltage. Yes, from 0 to knee voltage there is almost a zero current is flowing through the circuit. But as soon as we are going to increase the voltage beyond the knee voltage, current start increasing, and as soon as we are increasing it, the current is increasing. This was the part of the forward bias situation. This is the forward bias, and the on the next half it's a reverse bias situation. So what happens in reverse bias is, as you increase the current, as you increase the voltage in reverse bias situation, initially there is no change in the current and it is at 0 ampere. But as you go beyond certain level, at a certain stage a breakdown occurs. And when breakdown occurs, there is a large amount of current that is flowing through the circuit. Exactly, it is the breakdown or the PN junction diode itself too, and it flows a large amount of current. I hope this is clear, that you are done with the PN junction diode VI characteristics. Are you done with this? Are you? So let's conclude something very important, that if this current exceeds, I'm talking about the reverse bias current, exceeds the saturation value or rated value of the PN junction, then the diode will get damaged. And if reverse bias voltage is equal to the breakdown voltage, then the reverse current through PN junction increases suddenly to the saturation value. This voltage, as we discuss, is known as the breakdown voltage, up to which the corresponding current is called as the reverse saturation current. And from the graph, as we have seen and discussed also, that the reverse current is very small and the voltage is independent of the reverse bias voltage. I hope this is clear. Is it clear? Is it? Do you understand this? Any doubts up till now? Is there anything? No? Great. Let's look at quick questions. The question says, if reverse bias voltage is equal to the breakdown voltage, then the reverse current through PN junction increases suddenly to the saturation current. Then this voltage is known as this is what we call as the breakdown voltage. Next question. Reverse current through a PN junction blank suddenly to the saturation value. Yes, reverse current through PN junction increases suddenly to the saturation value. I hope this is clear. So is it clear? Are you clear with this? Are you sure? We want to discuss two resistance of diodes, and that's why they are keep changing. That's why we call generally as the dynamic resistance of a diode. So let's have a look what dynamic resistance of a diode is, or dynamic resistance, or we call this as a AC resistance of the diode. Basically, it is defined as the ratio of a small change in voltage delta V applied across the PN junction to a small change in junction current, because as you have seen the characteristic, it is something like this. So this is a very small change in the delta V, but there is a change in the current. So this ratio of this is, let's call delta V, and let's call this is the delta I, the ratio of this two. Yes, this was the voltage and this was the current. Basically, this is the VI characteristics of PN junction diode itself. Yes, so this is what we call as an RD. It's a delta V by delta I ohm. And in forward characteristics of PN junction diode, RD is independent of the V above knee point. and the value of the RD in forward bias beyond knee point is very low and quite high. It is quite high in reverse bias condition. I hope this is clear. Is it clear? Is it? Do you have any doubts in this? No? Great. So now let's summarize this and work for the numericals. That the situation is something like this, that when we used to deal with the biasing, we have two biasing. The one of them is the forward biasing, and the other is the reverse biasing. When we say it's a forward biasing, that means the situation would be something like this, that this is the situation, this is p-type material, this is n-type material. Let me draw for this as well. This is p-type, this is n-type. When we say it's a forward bias, that means positive terminal with the positive battery and n-type material with the negative terminal of the battery. This is the connection for with the forward bias. And for the reverse bias, p-type material with the negative terminal, n-type material with the positive terminal of the battery. This is what we understood by reverse biasing and forward biasing. I hope this is clear. Is it? Do you have any doubts up till now? Is there anything? No? Great. One more situation, that let's see. This is the case of the forward biasing. And this is the reverse biasing. That this is the symbol of the PN junction diode, as you understand that this is the battery. Yes, this is the forward biasing connection. This is the anode, this is the cathode. Anode would be at higher potential, cathode would be at the lower potential. In the case of the reverse biasing, it would be exactly reverse, that you are going to use this connection. Yes, that anode has been connected to the lower potential and cathode has been connected to the higher potential. So if I understood what happens next, then the next will be that this was the diode, and it is something like this. Look at this, and it behaves as a closed switch. And when I say it's a closed switch, for ideal diode, it is having zero resistance. But when we talk about the reverse bias condition, then it is just the breaking of the path. I hope this is clear. It means it's an open switch. And when I say it's an open switch, it is zero current, or I should say infinite resistance. It's a zero current, or it's in case of the infinite resistance. I hope this is clear. Is it clear? Is it? One more thing I want to mention is that if question has mentioned ideal diode, then we do not need to provide barrier potential that is 0.3 volt for silicon diode and 0.3 volt for germanium diode and 0.7 volt for silicon diode. So we do not need to provide barrier potential, and we can start conducting from 0 volt and onwards for forward bias. But if question has mentioned practical diodes, then we need to provide zero point 0.3 for germanium voltage, for germanium, and 0.7 volt for silicon diode. Yes, so if they have mentioned ideal diode, then we do not need to provide anything, that neither 0.3 neither 0.7, and we can start conducting from very beginning. But if they have mentioned that it's a practical diode, then we need to provide them a 0.3 for germanium and 0.7 for silicon diode. One more thing, when they do not mention anything, when they do not mention anything, that means they want ideal diode. This is the by default situation. I hope this is clear. Is it clear? So if they want that practical diode should be considered, they are going to mention it generally. And if they are not mentioning anything, that means they want that you need to deal with the ideal diode and go for it. I hope this is clear. So everything is clear? Everything is clear. Is it done? One more thing, that for ideal diode, FR, which we call, I need to write it full. For ideal diode, forward bias resistance is 0, and reverse bias resistance is infinite. And for practical diode, RF, which we call as in forward bias resistance, this is RF, this is RR, so very low, and RR, it's very high. I hope this is clear. Yes, so please keep this in mind, that when they say ideal diode, forget about the forward bias resistance, and for reverse bias it's a maximum, it's an infinite. And when they say it for a practical diode, the forward bias resistance would be very low and the reverse bias resistance should be very high. So after this much information, you are ready with the questions. Are you ready, guys? Are you? Great. So let's have a numericals based on this. This is the ideal diode and this is the battery, this is the current, this is 10 volt, this is 2 ohm. So the question says that for ideal PN junction diode or diodes, find out current passing through the circuit. So as this is the ideal PN junction diode, and as you can see, this is 10 volt, this is anode, this is cathode. So when one of them is the anode, another is the cathode, or I should say this is the P type material, this is the N type material. As P type material has been connected with a positive terminal of the battery, N type material connected with the negative with the battery. So this is the forward biasing, and as this diode is been forward biased, So it will behave as a closed path, something like this. So this is 10 volt, this is 2 volt. So this is 10, this is 2. So the current is equals to 10 divide, this is 2 ohm, sorry. So this is 10 volt, this is 2. So this will be equals to 5 ampere. I hope this is clear. Is it? Is it clear? Great. Let's look at the next question. The situation is something like this. This is one of the diode. This is the another diode. This diode, let's call this D1. This is D2. This is 10 volt. This is 2 ohm. This is 2 ohm. What I want to find out the current through this I1, I2 and I3. So the question is find I1, I2 and I3. So now what do you think? How will you do this? What can be done? As you can see this diode, it's an anode, this is cathode. Anode has been connected with the positive terminal, cathode has been connected with the negative terminal. So if anode is positive terminal connected with the positive terminal, cathode connected with negative terminal, this is the forward bias case for the diode D1. For the reverse bias, cathode is connected with the positive, that means this is the case of the reverse bias. So when it's a case of reverse bias, it will not allow any current to pass through this, but this will allow current to pass through this. So circuit would be if I redesign the circuit, it will something like this, that this is the closed path and this is the open path and this is the resistance, this is the battery. So this would be the situation. This is 2 ohm, this is 10 volt and this is I3. I hope this is clear. And as I2 equals to 0 because no path is there, that means I1 and I3 would be equal. So that means I1 is equals to I3, which is equals to V by R. And if it is a V by R, this is the simplest case of 10 by 2, which is equals to the 5 ampere. I hope this is clear. Was it? So do you understand this completely? Do you have any doubts? Is there any doubts, any confusion in this? Do you have any doubts, any confusion in this? Are you sure? Are you done with this? Pretty sure? Great. Let's work for the next question. Let's suppose question said that, let's first look at the circuit diagram. So this is the situation and this is what we can say, that this is 2 ohm. This is silicon diode. This is 10 volt. They said find out current passed through a circuit for practical silicon diode. So you want this current through the circuit, yes, as well as they mention as it is a silicon diode. So when they mention it's a silicon diode, it's a germanium diode, indirectly they say that you need to consider the knee voltage. And when you need to consider the knee voltage, what you understand is that within this 10 volt, this is 10 volt, first 0.7 volt would be the knee voltage. Yes, so at that point of time it is not going to conduct before this has been reached to the 0.8, 0.9 and onwards. So this current is equals to 10 volt minus of 0.7 because it's a silicon diode, divide by this 2 ohm, and this is equals to 9.3 divided by 2. This is the current that has been passed through the practical circuits. I hope this is clear. So do you understand this? Have you got this? Are you sure? Any doubts? Is there anything? No? Done? Great. Let's one more question. Suppose the situation is that this is one of the diode. This is the another diode. This is the battery and this is the resistance. Yes. This is D1, this is D2, this is 10 ohm, this is 10 ohm, this is a battery of 20 volt, and again this is the 10 ohm. Yes. They said diode D1, it's a silicon diode. D2, again it's a silicon diode. What do you need to do? You need to find out this I1, this I2, this I3. Yes, how will you do this? So as you can see this, that this diode D1 is in forward bias. Now you understand exactly what forward bias, reverse bias. So you can do it quickly. So this is forward bias situation. This is the reverse bias situation. And the D1 is in forward bias, D2 is in reverse bias. That means the, but this all are the practical diodes, because they have mentioned it that it's a silicon diode. Otherwise they are not going to mention the name of the diode or material of the diode. So this is indirect approach to tell you that please consider the knee voltage. So this, no current will be flowing through this. It's an I2 that is equals to 0, and if this path has been broken, that means this I1 and I3 would be the equal. So it's an I1 which is equals to I3, and this is equals to V divide by this resistance plus this resistance. But again I need to do this barrier voltage or cutoff voltage or knee voltage, whatever you call it. It's a V minus of VB divided by 10 plus 10, which stands to it's a 20 minus of 0.7 divide by this 20. It's a 19.3 divided by 20. Yes, ampere. I hope this is clear. Was it clear? Are you sure? So do you understand this completely? Do you have any doubts? Is there any clarity needed? No? Are you sure? Great. Now let's look at very interesting question. Suppose this is the circuit diagram, and we have two diodes. That, let me redraw. This is the resistance, and then it has been connected with the ground. Yes. Let's suppose this is the silicon diode. This is the germanium diode. Here we have provided a 10 volt. Let's say this is point A and this is point B. So what, and this, let's call this as a 10 ohm. Yes. So what they want, that find out potential at point B. This is the requirement. You need to find out the potential at point B. How will you do this? Take your time of 30 seconds and tell me what was your answer. Yes, what do you think? How shall we do this? If you are thinking that it is a 10 volt minus 1 volt, how 1 volt? It's a zero point 0.7 plus zero point 0.3, and this is equals to 9 volt, then you are absolutely incorrect. This is not going to work. If even you are thinking that it's a zero point 0.7 into zero point 0.3 divided by zero point 0.7 plus zero point 0.3, because it's a parallel combination of these two batteries, first thing must be clear that they are the practical diodes. Yes, so knee voltage would be always there, and if you are going to do this, then even this is not going to work, so please don't do this. So this all are the options which are not correct one. Now let me help you guys. What the situation will be, that once we provide 10 volt here, then this 10 volt will be available at this point, and as silicon diode will conduct after zero point 0.7 volt, and the germanium diode will conduct after zero point 0.3 volt, so it will start conducting at the early stage. So the thing will happen something like this, that when only the zero point 0.3 volt was available, this germanium diode will behave as this, and this silicon diode, this was the silicon diode, and this was the germanium diode. So as this starts conducting, this is point B, this is point A, and which is equals to 10 volt. So if someone asks me the potential at point B, then it would be equals to 10 minus of 0.3, which is equals to 9.7 volt. Now your question you may find that sir, after 0.7 volt even this will start conducting, but this will never get a chance to conduct, because once the current get a path which is a conducting one, it will never approach this for the current, because this is not the time dependent currents. I hope you understand this. So this is the potential at location B. I hope this is clear. Is it clear? So are you comfortable with this? Are you? Great. So now let's wind up this session over here. This was all about the PN junction diodes. I request you guys to please go through this lectures very seriously, because this unit is having capability to deliver the maximum amount of question if you are medical aspirants. Yes, if you see the previous year asked questions, it is having almost 3 to 4 questions each exams. They have delivered 3 to 4 questions in each examination, and within those 3 to 4 questions on every year, one of the question has been asked from this diodes. So this is very important. Please go through this, please revise this. Only this can save us, and we can have the questions of this topic. Thank you. Have a good day. Take care. Bye.